quick little recap. We started off asking interesting questions about infinity from a philosophy standpoint. Then we realized there's some practical applications, like when we're trying to figure out how big a circle is. That some of these questions, we don't have an ability to lock it down with algebra. We have to consider methods of approach and then run those methods of approach towards infinity. But towards infinity is not good enough. It'd be really great if we could run it to infinity, right? Or we could figure out what's going to be the end of that forever long list. So we avoid the exhausting process of making the method of exhaustion happen. Today, we're going to start to bring all this together, but it's going to require you all to kind of carry with me. So there'll be times in the class when I'm saying, this is a good thing to write down. There'll be other times when I'm going to ask for your attention up on the board so that you and I are calibrating to each other, that I make sure you understand what's happening, and then I'll give you time to write those notes down afterwards, okay? So just make sure you're kind of feeding with me. If you get confused, I need the feedback. I need y'all to be letting me know where we're at. All right, so we have, again, an estimate for pi at this point in history. We're in about the 1700s. At the 1700s, pi was not what you have on your calculator. Pi was 22/7. That was pi. Type it in your calculator, you get something pretty close to what we call pi right now, but that was the answer we had. Now, ironically, we had it from Archimedes' work. The interesting thing is that Archimedes' work was actually stored in the Library of Alexandria. And the Library of Alexandria is famous for having burnt down. Now, to put this in context, let me frame it this way. Imagine if I found a way to completely delete the internet. How much information would we lose? Everything, right? It'd be catastrophic. How do I know? Because it already happened in history. When we burnt that library, it was the biggest collection of knowledge in a time when knowledge was written down on scrolls and books, and reproducing them was expensive. So there was usually just one copy, and it all burned down. What that meant for mathematics is for 1700 years, we said pi was equal to 22/7, and nobody knew why. That's crazy. People were calculating how big things were and building structures, and no one knew where the number came from. Now, fast forward a little bit through history, and we're going to stumble upon a mathematician by the name of Bonaventura Cavalieri. Bonaventura Cavalieri is going to essentially rediscover the same approach Archimedes used, but without any reference or knowledge of how Archimedes originally did it. And we're going to take essentially Archimedes' method, which was good, but required a unique approach and very individualized knowledge, and we're going to make it simple. And it's what we continue to use today. All right. So, quick little reminder. What was Archimedes doing? Let's imagine Archimedes wants to figure out how big this area inside of a parabola is. Archimedes' approach is, let's fill it with shapes that are a pretty good guess, and then fill in the gaps with even better guesses, and then run that process towards infinity. And then when we eventually get tired of doing math by hand, we'll call that the best guess, and people will use it for 1,000 years. Right? Not fantastic, but pretty good for the times. So in this approach, specifically with the parabola, parabolas were common because parabolas are one of 4 basic shapes that describe shadows. And shadows were used to tell time with sundials. On top of that, we now know today, parabolas, circles, ellipses, and hyperbolas are the only ways that things are allowed to move in our universe. Things are only orbiting ever in ellipses, parabolas, circles, hyperbolas, or sometimes a straight line if there's nothing in the way. So this is a very interesting and commonplace shape. Also, it comes up in magnetism and electromagnets because they're talking about how different influencing factors affect each other. It's a very common shape. It comes up a lot, even though not a lot of us are told about this. Anyways, he comes up with an approach for triangles, fills in with triangles, gets a wonderful equation that I have printed off for you in your guided notes, is able to run that thing towards infinity, and comes up with a pretty good guess. Excellent. The difficulty is triangles are not an incredibly nice shape. Their equation is a little bit harder than we might like, 1/2 base times height. Also, Try finding the area of this triangle when it's not even placed in a decently good spot. It gets a little challenging. And it required a lot of creativity and a lot of brute force. We are going to simplify this. So we are going to replace triangles with rectangles. Rectangles are much better, right? Now it's just going to be base times height. Length times width, right? Much better than having to deal with triangles. We're going to fill in these rectangles going all the way across. So it becomes a pretty good guess. Now the question I have for you, taking a look at this diagram off in the bottom right, if I was to just figure out how big this rectangle is, combine it to that rectangle, this rectangle, all the way on down, would we agree that the red space is a pretty decent estimate of what's underneath the curvy space? I've got like 4 people nodding. Let's try again. Y'all help me out. Right? All right, so it's pretty close. How could we make it better?
Make the rectangles more narrow and ortho.
I like the rectangles becoming narrow, right? There's actually a lot of strategies for this one. One, we could fill in the gaps with triangles. That works out pretty well. In fact, we don't even have to deal with rectangles and triangles. We could just deal with them all as one big shape. We call this a trapezoid. So there are actually ways of estimating this using trapezoids. But I do like the idea of trying to make these skinny. Let's take a look at what that would be. If we make them skinnier, now do we agree that the red region looks closer to the curvy region?
Yes.
All right, excellent. So we've got our approach. We're going to make the rectangle skinny across a certain domain, and then we're going to run that. So let's start it where we're going to have them be nice, fat, tangible rectangles. Then we're going to try to write how we did that with math. And then if we have time, we'll try running that math to infinity and beyond Buzz Lightyear stuff. All right, so let's begin a little bit. We're going to add up a bunch of these rectangles. If you lose me, I'm talking about these rectangles right here. Okay? So let's begin. This very first rectangle looks quite flat. This rectangle here goes up a little bit. Next rectangle goes up a little bit more. Excellent. So what I'm going to be figuring out is that the perfect area, I'll call that A, is going to be pretty close to the area I estimate using 10 rectangles. All right. Again, there's a story behind the symbols, so make sure we're paying attention to the story. How do I find the size of a rectangle? Rectangles are length times width, so let's go ahead and make it a whole bunch of length times widths. All right, here we go. First rectangle would be width 1 times height 1. And then I would add that to the second rectangle, which would be width 2 times height 2. And then I would do that all the way until I get to my 10th one, right? Then I've got rectangle 1 plus rectangle 2 plus rectangle 3 all the way through. We should feel nice and comfy with this. This is literally us just putting in the math what we all felt was a good idea to begin with. Okay. How do I find the width? Well, let's imagine, just to make it easy, that if there's 10 of these rectangles, I'm going to split this whole 0 to 1, because that's my domain here, 0 to 1. I'm going to split that into 10 pieces. So how wide is every rectangle? 0.1 or 1/10, right? And that's going to be for every rectangle. That makes this nice and easy. So that's going to be 1/10 times the height of the first rectangle plus 1/10 times the height of the second rectangle plus ... 1/10 height of the last rectangle. Oh, starting to make some progress. It's going to get a little tricky here. This rectangle right here, actually, I'll use the last one. Let's use the last one. This very last rectangle happened because I went almost all the way to 1, and then I went up, right? But I didn't go all the way to 1. How far did I go? I went 1 rectangle shy, right? What do we get?
You're at 9/10.
9/10, right? I'm 9 of my 10th spaces over. So that one I'm at 9/10. Okay, so now I've got 9/10 is the x value. So if this right here is 9/10, how tall is that? This is a parabola, right? Y equals x squared. How tall would it be? Let's try it, right? This is an x value. If I want to get heights, which are y values, what do? Not multiply it by it, but maybe plug it in, right? Because this right here says if I have a sideways, I can turn it into a height. So if my sideways is 9/10, 9/10 squared should get me the height. Do we feel all right with this?
Yes.
All right, good. And I got lots of nods. I appreciate that. Thank you all. So we're going to take that 9/10, which is my x value, and then we're going to square it because that's what my function tells me to do. So now I've got 1/10, a whole bunch of these other ones. Let's figure out what this one would have been. This one would have been 1/10 for the width. And then if the 10th one, I'm going 9 rectangle widths over. The second one, I would have gone 1 rectangle width over, which I think makes sense, right? I go over 1 rectangle width and then I go up. So that's pretty good. 1 rectangle width, then up. Width of the first rectangle, no rectangle widths, up. How do we feel on that? So this would be an estimate for the curvy region using 10 different rectangles. Is it going to be perfect? No, because a curved thing is not a bunch of rectangles. Is it pretty decent? Sure, but we're not in the business of pretty decent. We want to get to perfection, right? Now to do that, we're going to have to take everything we just had on the paper. We're going to have to bring it back into the symbols from whence it came. Okay, so if we feel good on this, then we're going to keep this off to the side as a reference, and we're going to try to rewrite it using just the variables. Because this, if you plug it in your calculator, comes out to about, what does it come out to be? Let's say about 0.32-ish, if I remember correctly. Okay, and again, you can do this in your calculator, right? But it's going to be rectangle, 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 and then addition, and then smushing it, and then submitting that for your final answer, right? Exhausting. Because it's the method of exhaustion we just tried to do. Now we're going to try to make this a little bit clearer. All right, so let's do a little bit of housekeeping here. Choose a different color. All right. So let's begin. I think we are pretty good here. I felt pretty good. Here I feel pretty good. Let's do this one. Let's try to make this one a little more explicit about the how we got there, not just the what we got. We got the 1/10 because we took the domain we were looking at and we split it up, right? We went from 0 to 1, we took that into 10 pieces. So if I wanted to split it up into 20 pieces, I would have split 1 into 20 pieces. 200 pieces, 1 into 200 pieces. N pieces, 1 into N pieces. So I can go ahead and write this. We'll say 1 over N H1 plus 1 over N H2 plus ... 1 over N H. I don't have 10 anymore. I have N of them. Very nice. Okay, that's pretty good. So that's that line translated. Let's translate this line. Here, I was trying to figure out the heights. The heights, I had to go over a certain number of rectangles and then up. Do we remember doing that? Certain number of rectangles? Okay, so let's see if we can make that look. That would be, so I still have my 1 over N for the width of each one. And then I went over, the first one was 0 rectangles. I went over 0 rectangles. And then I squared wherever that landed me. And then the next one, I had the 1 over N width, and then I went over 1 rectangle. And I squared that. And then I continued that all the way until I would get to the N. I would have 1 over N, and then I would have gone over 1 less number of rectangles. So this would have been N minus 1 rectangles, and then squared it. So again, I'm just translating it to the variables that we got everything from here. Is it fair for me to say that every single one of these things has a 1 over N? So we could factor that out, right? And in fact, 0 rectangles on up, that would have been just 0, what's 0, the rectangles? Oh, the rectangles were 1/10 each, or 1/nth each, or whatever. Okay, so I could actually make this 0 times 1/nth for the rectangle squared plus the 1n came out. I've got 1 rectangle, that's 1 rectangle width squared plus all the way until I got to n minus 1 rectangle widths squared. At this point, I'm going to pause for a moment because some people might be scribbling furiously. Do we feel good on where everything's coming from? Right? Formulas are working for me. I'm not working for the formulas. Right? I control the math on my paper. Okay, well, this one goes away. This would be 1n squared. Okay, so we've got 1 over n. That goes away. The next one would be 1 over n squared would be 1 squared over n squared. So pretty good at that. And then the next thing would be 2 squared over n squared, 3 squared over n squared, all the way on down to n minus 1 squared over n squared. Pause there for a moment. Go ahead and give me some indications. Thumbs up. We're following still. Thumbs down. I lost you somewhere in the algebra. Because I got a lot of people coming in with the algebra questions. That's okay. This is the time to ask, right? This is the opportunity. I budgeted into this class. Where did I lose you? Yeah.
Okay, so is this kind of tying in with the whole sigma sums thing that we did?
Aha. Yeah, well, in a second. Yep.
Right.
Good. Which I'm taking you're recognizing because you're starting to see a pattern, right? A pattern of addition. And we've worked with patterns of addition. Good. Is it okay for me to say every one of these has a 1 over n squared in it, and n squared on the denominator? So I should be able to factor that out as well. I could pull all of those out, and I have 1 over n cubed. And then I have a 1 squared plus all the way to n minus 1 squared. Yeah. Because I had another n right here in the front. So that one n on the denominator with these 2 n's on the denominator each gives me a total of 3. Good question. I like it. Well, this says I'm adding a bunch of squares, right? If only I had a formula that we'd explored where I could add a bunch of squares. Oh, wait, we did in the summation chapter, right? In the summation section, we talked about 1 squared plus 2 squared plus 3 squared. We got a formula for that allows us to run this for however big we want. That formula, if I remember, came about from us making a bunch of lopsided pyramids that stacked together to make a box, and the box had certain dimensions. So I think that all came out to be what? N by n plus 1 by n plus a half over 3. I think that's what the formula came from. Oh, but this one doesn't go up to n, it goes up to n minus 1. So I need to make these n minus 1s. N minus 1, and then n plus 1 minus 1 just makes that go away. And then n minus 1 plus a half makes it n minus a half. All right. Again, I'm pausing for a moment. We feel good? All right. Let's keep it going. I've got a 3 in the denominator, might as well pull that out. Or let's just do a little side work. Let's try to simplify this whole numerator, doing a little bit of simplification off to the side. N minus 1 times n minus a half. Lots of distribution here. I could do this one distributing in, maybe. Why not? N squared minus 1/2 n. And then n minus 1. I could do foiling. Or remember, if foiling is something that's not always working for you, or you fall into that trap, this is also something we could represent with that rectangle diagram, right? We can make this be dimensions of n minus 1 by n squared minus 1/2 n. That's another way of doing it. This is how I like to do it. Keep it where it makes sense to me. So I can go through and either by doing my little rainbow arcs or by simplifying this all out, we have n cubed minus 1/2 n squared minus n squared plus 1/2 n. So I think that that entire top is going to simplify out to n cubed minus 3/2 n squared plus 1/2 n, where I'm still divided by 3 and an n cubed. Yes.
Where'd the 3n cubed come from?
Came from the fact that I had an n cubed I needed to multiply in and keep on the denominator, and I had a 3 already there.
Oh, okay.
Good, I like this. See, this is this is where I'm looking for, right? Play off me, I'll happily clarify. Follow along and copy. I'm gonna lose you and none of this is gonna mean anything. All right, we still good? All right, yeah, please.
So,
I could do it to each thing on the top, right? In fact, that's what I'm gonna do next. So right now, I'm just simply saying everything has yet to be divided, so it's everything still over. If I want to do that division, let's do that division. All right, great. See, this is naturally motivated. I like it. And I like how we were just talking about that. It is, again, the symbols have meaning, right? This means everything needs to be divided by n cubed. In fact, everything needs to be divided by 3n cubed. So let's do that. The first thing divided by 3n cubed would be the 3 n's on the top and the 3 n's on the bottom that could cancel and leave me with 1/3. The second thing, I have 3/2 divided by 3, that would be 1/2. So I've got minus 1/2. And then I have 2 n's on the top, 3 n's on the bottom. That's going to leave me with 1 end balance on the bottom. And then the last thing, I've got 1/2 divided by 3. That's going to be 1/6, where I have 1 n on the top, 3 n's on the bottom. That's an n squared. How do we feel? Now, admittedly, we just did like 25 straight minutes of simplification, right? Like, I'm not saying this is super easy. However, it does look a lot better than it used to look. Was it worth it? Maybe, maybe not. Like if we're doing n equals 10, it might have been just as quick to do 10 different rectangles and combine them, right? However, take a look at this. Let's try some things. Let's make n equal 10 and see how good my guess was over here. N equals 10. Let's plug that in. That would be 1/3 minus 1/20 plus 1/600. Who wants to try that for me? All y'all with calculators, what do we get? 0.285? 0.285. Oh, I was a little off. Bummer. Sad face.
Yeah, I got the same thing.
Bummer. Maybe I just was waiting for there to be more rectangles. All right, let's crank this up a level. Let's make n equal to 100 rectangles. That's the strategy, right? So now I've got 1/3 minus 1/200 plus 1/60,000. Oh, so maybe I just got ahead of us. 0.32385, something like that? 835. Did I just do 100 rectangle math in my head? No, better than that. Because notice, what are we playing with right now? We're playing with the method of exhaustion. Do we all feel a little exhausted plugging in these values over and over and over again? You want to keep playing this game for a long, long time? But we could, instead of doing it through this brute force strategy, run the logic and let the logic carry us further than our calculators ever could. Pause for one moment, I'll be right there. So let's take a look at this. If I make n equal to super big, 1/3 stays as 1/3. Do we agree?
Yes.
1 divided by 2 bigs is going to simplify to what? Or small, right? Very, very small. 1 divided by 6 times a big squared is going to simplify to very, very small. So if I run this towards infinity, The 1/3 stays alone. The small becomes the smallest. What's the smallest size? What's this smallest size? What's our perfect answer?
How about that?
Right? Like, I want to take a moment and, like, right now, okay, that was a lot of brute force math. I want to take us back in time a little bit and imagine, because I have already proved for you in this class that most of the numbers on the number line are not nice numbers, right? In fact, if you were to throw a dart at the number line, you are 100% guaranteed to hit a not nice number. This is a shape of nature that we can see in a variety of places all around us, and it has one of the few nice numbers. Do you start to see why people like the Pythagoreans might have become religious fanatics around math? Like, they're all of a sudden looking around like, my golly, there's patterns here. Like, there are rules that govern nature. We all thought that if we just said the wrong thing, Zeus would smite us. But no, in fact, we can predict where certain things come from because nice numbers happen. Big, big, powerful revelation that this actually worked out and worked out quite nicely. Because pi didn't work out nicely and e didn't work out nicely, but this one did. That's weird. So we've now got strategies. If you want to get an estimate for something, just smash a bunch of rectangles together. Like, you can just make that happen, right? Like, go do rectangles like you would have way back in algebra, like pre-algebra, like just make some rectangles. If it starts to get exhausting, maybe start to work the equation. If you've already got the equation, why wouldn't we blast that equation towards infinity and then get perfection? And we can do this over and over again, not just with certain shapes, where I fill them in with certain other shapes in a very particular pattern. This was rectangles. I could do this with anything. Very powerful stuff. All right, there was a question over here. Did I get to it?
Yeah.
You feel good? Okay. All right, let me pause there for a moment. Are there any questions? All right. Yeah, go ahead.
So I might be getting ahead of us here, but so would the equation, the whole n equation we have then change depending on what equation our parabola is? Then we'd have to redo all the simplification.
Yes, but let me adjust the language a little bit. It would change based on what equation our curve was. Because a parabola is a very specific kind of curve. But if it was, let's say, x cubed, which is also curvy, then instead of plugging it over here and squaring it, we would cube it. If we wanted to plug it into an x to the fourth, then we would x to the fourth it. We would raise it to the fourth power. If we wanted to square root it, we would square root it. So we can use this with any strategy at all. Some of them are easier or harder than others for sure, but any one of these strategies works. Also, a few other things to note from this, which is why the story is the most important. We split up 1 over 10 pieces because 1 was the distance I was considering, the domain I was considering. If I went off to 2, then I'd be splitting 2 amongst a bunch of rectangles. If I was looking at the distance between 3 and 13, that distance would be 10 that I'm splitting up a bunch of rectangles. So again, it's not about necessarily the formula, it's about where the formula came from, right? That's always more powerful. But we do have a formula that we can now capture from this. So we first need to kind of define this thing. We just found perfect area of curvy things. Again, let me reiterate how impressive that is, right? If I ask you how big is a circle, the best estimate that anybody had before this was to put a box around the circle and say it must be smaller than the box, and put a box inside the circle and say it must be bigger than that box. So it's got to be somewhere between. And then all we did was made the boxes better estimates, and we said it has to be between better estimates. But no one pinned it down, right? Similarly, if I ask you how big your hand is, you take your hand, dip it in some ink, and slap it on paper, you get a handprint, right? If I ask you how big is that, right? We know it has size. It takes up space. How much size? It's very difficult to answer that question without saying about, right? It's definitely going to be bigger than anything that fits inside it and smaller than anything that it fits inside of. But how big are these things? So this is actually the first time in your life that you can actually go out and tell somebody what area is, right? Because area is defined by the process we just created. Make an estimate, run that estimate method towards infinity. We call that an integral. So an integral is area. That's where it came from. It has the exact same root as integrity and our complete numbers that we called the integers. So this is literally a word that means complete area. That's what it is in its name. We'll use it for plenty of things throughout this class in the same way that I've been using rectangles like crazy. But this is what it is. Everything else is just how we'll use that model creatively. So let's do a little bit of a recap. What did we do? We said the true area was approximately the area of a bunch of rectangles added together here. Right? We feel pretty good with that? All right. Why did I choose squiggly equals sign here? Why didn't I just do equals? It's approximately, right? As long as I try to estimate curvy things with a certain number of rectangles, that will never work out well. But we did know how we did that calculation. We replaced areas with widths times heights. That worked out fine. We ran that through how do I find the heights and how did I find the widths, but at its core, it was widths and heights. But you want to see the proper way of writing it? There it is. Notice, now it's a solid equals. It doesn't say squiggly equals anymore. Why doesn't it say squiggly equals? Because it's exact as a result of what? It's not an estimate anymore. If it was an estimate, I would use the squiggly equals.
Approaching infinity.
What approaching infinity?
Well, the end values.
What's n mean? Keep going.
Number of rectangles?
Number of rectangles. Wait, hold on. I thought that we started off by saying our strategy was to make the rectangle skinny. Did we ever make the rectangle skinny? Yes, but we did it through a creative way. We didn't necessarily focus on making the rectangle skinny. We just tried to shove a whole bunch of rectangles into a set amount of space, and that forced them to be skinny, right? We can go back to here. Remember when we were splitting up 1 over 10 and then over 100 and then over 1,000, right? So we made the rectangle width skinny because we were tracking more and more rectangles. So n was the number of rectangles we were trying to shove into this space. And sure enough, when we make the number of rectangles be a forever number of rectangles, those forever number of rectangles have to be forever skinny. The forever skinny rectangles approach our curve, we've got perfect area. It's rectangles. It was just rectangles where we were empowered by using variables instead of numbers. Once we had variables, I could run that thing to forever. The moment you put a number in there, I was locked. So variables were powerful. They allowed us to look at the behavior, the trend. This is how you'll see it in your book. Limit as n approaches infinity of delta x. What's delta x mean? It means how far I go across on x, the change in x. Why did we go across x? Because we were trying to make rectangle widths, right? So delta x is literally your rectangle width. That's what it means. What about the function? Why did we plug things into functions? It turned it into a y value, which we cared about for the height of the rectangle, right? So that's exactly it. The function values are all the heights of the rectangles. So this down here looks formal and intimidating, but if we look behind the symbols, if we look for its meaning, this just says, shove a whole bunch of rectangles into a place such that I get smaller and smaller widths when I divide it up by a bunch of rectangles, and all those rectangles' height depend on the curve. So this is again where the story is so much more important than the symbols, because the symbols can be intimidating and rough, but you all have been playing with rectangles for years. So use the rectangle knowledge you have, build it up from there. All right, I've got some time if you all want to stick around and clarify some notes. You should not leave today with any questions that you haven't asked. Otherwise, you're certifying and agreeing that you're going to let that come and kick you again. So stick around and ask the questions that are in your notebooks so that I can help. We've got time. Otherwise, next time we're going to talk about, is there a way to do this faster that doesn't take me 40 minutes of class time? I'll see you then.